So we have these great pictures of how your rocket went up, 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 and we have some idea of how high they went, but we aren't sure exactly who won our height competition. We're going to need to figure out some things about the rocket's energy, its kinetic energy and its height potential energy, and hopefully we'll be able to sort out who won the competition by looking at some of those observations. So our goal here of looking at the frame-by-frame video analysis is going to be, at first, to figure out the kinetic energy of your rocket. And we know the formula for kinetic energy involves the mass of the rocket. You put them on scales, we know how much they weigh. But we also need to know how fast they were going, and how fast they were going at every stage along the way. They sped up and then they slowed down. They weren't going the same speed the whole time. And we need to be able to track some of those changes. Velocity is, of course, also known as speed, so we'll just treat the two words the same right now. And you might have remembered from your middle school classes that distance divided by time gets you at speed. Of course, in our rockets, we said that we're going to be looking at distances measured as the change in height divided by the change in time, how much time has passed. So we've got those things ready for ourselves. And the big picture, here it is again, change in height divided by change in time gets you velocity. We need to figure out how to figure out the change in height and how to figure out the change in time. And that's what this and these instruction sheets are all about, and that's what I'm going to walk you through right now. So and here it is again, our equation involving the change in height and change in time. So the easiest thing to do is, of course, to start with the times, because you can determine those just from the video camera settings. Film is basically, or video is basically just a series of camera images taken one right after the other, and at regular intervals. And you can set your camera to take pictures at usually it's about 30 frames per second for most typical video cameras. And for some of our high resolution images that we're going to be looking at from your video analysis, you might be looking at cameras set to take pictures 60 times each second. So that's time. The height, well, it requires a little bit more in the way of calculations. To determine heights, we need to start by choosing a reference point, measuring the height above that point on the page, converting that height on the page to a height in real life, and then taking our heights and our times, dividing those out. That's going to get us a speed, and since we'll be using units of meters for height and seconds for time, that's going to give us a speed in meters per second. Not a very familiar unit, so we'll be converting that from meters per second to miles per hour at the end. Those are the steps that we're going to follow. They're all laid out for you on this instruction sheet. And this page here walks you through column by column each one of those steps, and then of course there's acceleration that we'll get to a little bit later, not in this set of videos. So let's start at that first step, choosing a reference point. We talked about this in class, about how it really doesn't matter where you choose your reference point, where you measure from on the ground and where you measure to on the rocket, as long as you are consistent the whole time. So it might be easiest to start off by, I like to sort of measure from the rocket's launch pad, and I'll draw a line all the way straight across on that, and that's going to be my reference line. Or reference points, a series of reference points. I'm going to measure to the bottom of the rocket because that's going to make it easy for me to figure out this very first frame, frame 0. Well, how high up is it above the launch pad in frame 0? Well, it's right on the line, so I'm just going to write a big 0 right there. For times, let's go ahead and do those actually before we go any further. This is frame 0. It's taking place at time 0, that's easy. But we can go ahead and go right down. Remember, the camera's taking pictures every 1/30th of a second, so the first one is 1/30th of a second. You can convert that into a decimal by doing 1 over 30 on your calculator, and you get 0.0333. 2/30ths of a second, we can just plug them all in right now. 0.0666, and then rounding up to 7 on that last digit. 3/30ths, that's easy, that's 1/10 or 0.10. 4/30ths, 0.13333, and we can go on and so forth down there. We have times, we have a reference point. We need to now measure heights above that reference point on the page. and we're going to use the ruler. Our very first point here is just, our rocket, the bottom of the rocket is just barely off the ground. I'm going to put 0.1 centimeters. Our second point here is, let's see, that is about, it's just a little bit less than 1. I'm going to put 0.95 centimeters. Carefully measuring our next spot here. That looks like it's a little bit less than 2.4. I'll do 2.35 centimeters. And then here in frame 4, we'll go up even higher. And 3.8, no, a little less than 3.8. That's 3.75 centimeters. And the more precise we make these measurements, the more careful we are, the more accurate our velocity results are going to be. So we figured out how high these points are on the page. This one here we said is, in frame 2, 0.95 centimeters on the page. Here it's just barely 0.1 centimeters. But how high is that in real life? I mean, 0.95 centimeters is a tiny amount. This rocket's way up off the ground in this picture, and we need to figure out how much that is in real life. To make these conversions, what we're going to have to do is we're going to have to figure out something on this paper there where we know how big it is in real life. And in this particular case, we've been given a meter stick that's in this picture, and it's 1 meter tall. And it's the same height in every one of these pictures. So 1 meter tall in real life is, how big is that on the piece of paper? Well, let's go ahead and measure that. And I get 1.25 centimeters on the page. And that's true in frame 0. It's true in frame 1. It's true in frame 2. It's true all the way across. So we can go ahead and use that information to make a proportion problem. In the frame 1 here, our height on the page is 0.1 centimeters. How big is that in real life? I don't know. Question mark meters in real life is 0.1 centimeters. Now we have a proportion problem, and we'll be able to solve this using our simple standard rules for proportions, which is going to be cross-multiplying. Let's go ahead and cross-multiply here. 1.25 centimeters times question mark meters equals 1 times 0.1 centimeters. 1 meter times 0.1 centimeters. We are trying to get this question mark all by itself on one side, so let's get rid of 1.25 centimeters on that side by dividing by 1.25 centimeters. And whatever we do on the left side of an algebraic equation, we have to do to the right side, so we'll do that there. Over here, these cancel out, and we're left with just question mark meters equals 1 meter times 0.1 centimeters divided by 1.25 centimeters. You'll notice that we have the letters cm on both sides. Those cancel out, and we're left with just 1 times 0.1 divided by 1.25 meters. It's the only unit that's left. So now we can pull out our calculator and do 1 times 0.1 divided by 1.25. Hit the equal sign, and we get 0.08 meters. That's not very much, but that makes sense. That doesn't look like it's very high off the launch pad in that first frame, does it? This is great because where did this, let's take a look at this last step here right before we have the answer. We have question mark meters equals 1. Where did this 1 come from? Well, that's the meter stick. That's the meter stick 1 meter tall in real life. And this 1.25, that came from the measurement on the page. These two numbers stay the same all the time for our particular size of piece of paper here. This box here is going to change in every frame. So the next frame, the height is not 0.1 centimeters off the line in the page, it's 0.95 centimeters. Instead of having to go through that whole proportion problem again, for frame 1, we're just going to do question mark meters equals 1 times this box, and now inside this box is going to be 0.95 for 0.95 centimeters. It's the measurement right there. And we're still going to have to divide by 1.25. We can type that into our calculator. 1 times 0.95 divided by 1.25 equals 0.76 meters. And that's the answer that we're going to put right here. 0.76. Oops, and I forgot to put the answers for this previous one here. 0 is still 0. That's the height. And now we have 0.08. So let's take a look at where we are on our grand plan here. We've got times, and we now have heights, all the way down to the height in real life. So now we're going to have to look at the change in height and divide that by the change in time. So we're looking at the change in height divided by the change in time. So coming back here to frame 0 and frame 1, how much has the height changed in real life? Well, it's now 0.08 meters. It was 0 meters. So what we're going to do is we're going to do change in height divided by change in time it's now 0.08. It was 0. And we can do the same thing for the time. It's 0.03333, and it was 0. And unit-wise, this is measured in meters, and this is measured in seconds. Everything on the top is in meters, everything on the bottom is in seconds, so we're going to be in meters per second, which is a unit of speed, which is good. And for this one, this is going to be 0.08 over 0.03333. Let's pull out the calculator. 0.08 divided by 0.03333, and we get 2.4 meters per second. We've got an answer for this here. We should also fill in that the velocity at the very beginning, of course, when it's sitting on the launch pad not moving, we can fill that in at 0 already. But look at what we did. We took this frame and subtracted off the height of the frame before, and this time, and subtracted off the height before. Let's do it again to get the velocity that we're going to put for frame 2 here. It's not actually the velocity in frame 2, it's what's the average speed during this time here. How many meters per second? Or eventually we'd like to know, so we can think about it more easily, how many miles per hour. So in order to get that speed, how much the speed in between these two frames, we're going to need to know the height in this frame and how much it's changed from the frame before, and the time in this frame and how much it's changed before. So let's go ahead and do that now for frame 2. Still need change in height and change in time. I'll abbreviate them. And the change in height here is going to be 0.76 meters minus 0.08 meters divided by 0.0666 minus 0.0333 seconds. You can quickly subtract off 0.76 minus 0.08. On the top is going to be 0.68 meters, and that takes 0.03333 seconds. 0.68 divided by 0.03333, and we get 20.4 meters per second. Frame 3, which is really going to be looking at the change in height between frame 3 and frame 2. Okay, so looking here now, we know that the height in frame 3 is 1.88. The height in frame 2, the frame right before it, because we're looking at how much the speed has changed in between these two frames. We're not looking at the average speed overall for the whole time. We're looking at how much it is during just this little time block, because remember, this rocket's probably going to be speeding up and then it eventually will slow down. So we've got that over 0.10 minus 0.06666 seconds. On the top, we're going to take 1.88 minus 0.76. We get 1.12 meters. And on the bottom, you'll notice a pattern here. It's always a 1/30th of a second in between these two frames because they're taken at intervals of 1/30th of a second. We can do this in our calculator. 1.12 divided by 0.03333, and we get 33.6 meters per second. So our rocket looks like it's speeding up. Let's do one more frame real fast. Frame 4 is going to be 3.00 meters. There's its height in real life, minus the height in the frame before. Divide this up. Three minus 1.88 is 1.12 meters in this many seconds. And I get, oh, look at that, huh, it's the same as it was before. The speed hasn't changed. Our rocket hasn't started slowing down very much yet. And you can look at here, in between frames 3 and 4, it looks like the rocket is just running out of fuel here. So it's not getting any faster because there's no extra fuel, and not much time has happened for gravity to slow things down yet. So maybe it's not surprising that the speed is staying the same. But you know that as we go from frame 4 to frame 5, this rocket's going to start slowing down because gravity is going to start slowing it down. And we'll take a look at that. So we have a whole bunch of measurements for meters per second. There is one more phase we need to do, which is we need to convert from meters per second to miles per hour, because I quite honestly don't really know how much 33.6 meters per second is. And to do this, we need to know a simple fact. We need to know that 1 meter per second is equal to 2.2 miles per hour. And that's a fixed ratio. It's just like that there are 12 inches in 1 foot. There are 3 feet in 1 yard. It's a definition of these units. And we look it up somewhere, and this is a fact. And it's a fact always. So if it's a fact always, we'll be able to use it as a fixed ratio in a proportion problem. So now, if we want to know how many miles per hour our rocket is going, we can plug in a little box here and put a proportion problem. Has the same thing on the top and the same thing on the bottom. And here in our box, let's say we want to figure out how fast 2.4 meters per second is. 2.4 meters per second. We're going to solve this problem like we do all proportion problems. We're going to cross multiply. That's going to be 1 meter per second times question mark miles per hour equals 2.2 miles per hour times 2.4 meters per second. I'm going to keep that box because this box comes from our measurements. The 2.2 and the 1 meter per second come from the definition that we had to memorize or look up in the beginning. So let's go ahead and try and see if we can get question mark all by itself. How do we do that? We divide by 1 meter per second. Whatever we do to the left side, we do the right side. Cancels out on that side, and we're left with question mark miles per hour if we have our meters per second, we do actually have something cancel out here. The meters per second do, and 1, you can divide by 1, and just remember you get to ignore that. That's the great thing about dividing by 1. 2.2 miles per hour times a number in the box from our measurements, and divide by 1, ignore. So here's this simple thing. So here in our very first frame, we have 2.2 times 2.4 equals 5.28 miles per hour. And remember, we can write that in right here. 5.28. Note how I wrote the 0 miles per hour, because converting from 0 meters per second to 0 miles per hour, that's pretty good. For frame 2, we have 2.2 miles per hour times 20.4. Get the calculator out. 2.2 times 20.4. That equals 44.88 miles per hour. We can plop that in. We can do one more velocity here. 33.6 times 2.2. We're going to get 73.92, and we said that it was the same in the next frame. And there we go. We now have gotten from this picture, we now know that our rocket was traveling 0 miles per hour here. It went up to 5 miles per hour in this frame. It sped up to 45 miles per hour. Then it got up to 74 miles per hour, stayed at 74, and you can figure out for homework what happens to it after that. And you can check your answers against what we've got on the Moodle website to try and make sure that you're checking and getting all the answers right. We'll deal with acceleration next time.